teacher.
No, 7.2 because I'm dividing by 5, right?
But the addition is bad.
Ah, okay, 0.36. Yes, you're right. You're right. Sorry. 0.36 divided by 5. Thank you. Is 0.
I have a question.
Yes.
The more the client gets, have an accident, the more the Q increase, or no?
Oh, well, that's another discussion because that's about how an insurance company decides to give incentives to clients. Yes, they usually calculate a certain premium, but it's not. Some companies do this, some others not. Some companies calculate a general premium, and then they say, for next year, if you have no claims, no accidents, because you were very careful, I will give you a discount on your premium. Okay, that is kind of an incentive for clients to be careful with their cars, because it might be in some cases that people say, okay, I have insurance, I can drive recklessly, right? And it doesn't matter if something happens, I have insurance. And of course, insurance companies do not want to promote that. They want exactly the opposite. So some companies, in the way they calculate their premiums, they may consider an incentive, a discount for those clients who in the previous year didn't have any claim. They will give you a discount. If you have some claims, you will get the normal premium. Okay?
Yes.
Okay. So let's say we said, okay, from here I can get this average, okay? This average proportion of having this claims rate. So this is the claims rate. This is a very simple way just to explain where do we get this, right? So the probability of having, for any car, of having an accident, of having a positive claim is approximately, according to this historical information, 0.0072 from the last 5 years. That's the way you will estimate this part, okay? But now, if you want to model to get to estimate f of xj, given xj positive, you will look to the claims, right? So, because here we are just taking account of the number of claims, 5, 8, 3, 11, 9, okay? But each claim was from a different size, of course, because it belongs to a different accident, to a different car, to a different situation, right? So probably if here we have 5 claims, each claim had certain amounts, right? In this case, if we have 5 claims, let's say the first claim was 15,000. The second claim was 38,000. And so on, okay? So we have amounts, 5 different amounts of claims. Then here we will have 8 different amounts, okay? Probably 29,000, 58,000, 350,000, probably the car was stolen, whatever, okay? So here you will have amounts of money, okay? You will have 36 different amounts of money. But with these amounts, we use those to estimate this conditional distribution. Because all these amounts are conditional on the fact that there was a claim, that there was an accident. So with this historical data from these 5 years, 36 claims from the amounts of those 36 claims, we use that information to feed a probability distribution to this data. Okay? And this will be an approximation of the conditional distribution of xj, given that xj is positive. Is it clear now? Where do we get the information from? I mean, this is quite simplified example, but it's just to give you an idea. Where do you get the information from? Estimation.
Yes,
from, okay, it's information from historical data. So now, being clear, where do we get the information from? This formula makes sense, right? Because I just explained how can you estimate QJ from the company's data? How do you estimate the conditional distribution of xj given xj positive? And then we have a formula for the non-conditional distribution of xj, which was the purpose, right? Because we said we need an individual policy model. And that means I need to know, to estimate the probability distribution of xj, non-conditional. But what happens in practice is that conditional probabilities are easier to estimate than non-conditional. I know that when we learn probability, it's the other way around, right? We start learning how to calculate probabilities and properties and so on. And then we learn that after that, we learn the concept of conditional probability. And we have a formula for the conditional probability in terms of an intersection divided by the non-conditional probability. But in practice, it's all the way around. Usually, the information we have access to, the data we have access to, is usually has some conditioning behind. Okay, that's the thing. So it's very common in practice that you are able to estimate conditional probabilities, and then you have to find a way to estimate or to model non-conditional probabilities. So this formula 3, which was the last one we discussed last class, that's a good example of it. Okay, is everything clear for everyone about this formula and its importance? And more important, I try to explain in a very simple way, how do you get the information from to estimate the QJs and the conditional distribution? Okay, good. Now, let's take a look to a graph of this, just to have the idea of this, right? Let me go to the Blackboard again. So, a page. So we said that we may also, well, probably I should write it again. It's going to be fast. So the formula was 0 if x negative, of course, 1 minus qj if x equals 0, y minus qj, no, sorry, 1 minus qj plus qj times the conditional CDF given xj positive. If x is greater than 0 and less or equal than tau, remember, this is the policy limit. And 1 if x is greater than tau.
teacher, I
So,
have another question.
yes.
The x evaluated in the conditional CDF, it's xj or only x?
It's only x. xj is just a label. It's like when you write, let's say, f of y or z. This means the probability of random variable y being less or equal than c, right? So in this case, if we write f of xj evaluated in x or any other value, this is the probability of xj being less or equal than x, where x is any real number. Remember that the domain of any CDF is always the whole real line. Okay? And then if you evaluate the conditional CDF of xj given xj positive in x, then this is the probability of xj being less or equal than small x, given that xj is positive. Okay? But this x is any real number. Is that clear?
Yes.
Okay, good. So, let me erase this. So let's make a sketch of a graph for this. Say, something like this. So we will have 0 here, x, let's say tau is, so I have a bar here. Sorry. And have tau 1, here we will have f of xj of x, non-conditional. And we said that qj is usually going to be a value closer to 0 than to 1, right? Because it's the probability of having an accident, which usually is very, very low. So if qj is very close to 0, 1 minus qj is very close to 1, okay? It's even closer than this, but this is just for the sake of this graph, okay? And I think that's it, okay? Just a moment. Okay. So according to this formula that we got, it's going to be 0 for x being negative, right? Because xj never reports a negative value. It's a claims random variable. It only takes non-negative values. So that's why we have 0 to the left. So let's put 0. Okay. But then we have a jump, a first jump. From 0, it jumps to 1 minus qj. Because the probability of reporting 0 is exactly 1 minus qj. Because qj is the probability of reporting something positive. So the probability of 0 is 1 minus qj. So here we have a jump. And exactly in 0, it takes the value 1 minus qj. And then from here, it may start adding to 1 minus qj. This function is non-decreasing, right? Even multiplied by a certain qj. So it will start increasing a little bit. Right? And then we have another jump, right? And then we have another jump. Here, in tau, it jumps to 1. And then it remains constant there. Okay. Okay. So this will be a typical graph of the distribution function of an individual policy model. And clearly it's mixed type, right? Non-continuous, it has two discontinuities, at least two discontinuities, at 0 and at the policy limit. Here, in this case, it's going to be continuous, probably, but it may have some jumps here. That depends on the product, okay? But since these are claim amounts, if it's not continuous, it's going to be something close for being continuous, because here we start with claims amount, but none of them will go beyond tau, right? Because tau is a policy limit, assuming that tau is the same policy limit for all the cars. And then we have a final jump, okay? Because with probability 1, the total claims will not exceed tau, because that's a policy limit. The insurance company will not pay more than tau. Even though if the damage was higher than that, the insurance contract says the policy limit is tau, 1 million pesos, 2 million pesos, okay? So that's the maximum amount that is going to be paid by the insurance company. So that's why I told you, it's very common when you start discussing models for insurance that you will end up with models that have a mixed type random variable model, right? It's not a step function. Here we have 2 steps, but this one is not constant, okay? So this is the first idea. Any questions so far? Is it clear? And we don't have PDF, we don't have probability density function, we don't have a probability mass function, but we need to make calculations with this model, with this random variable xj. Remember, xj represents a particular insurance contract, okay? So if we want to make calculations about that insurance contract, we need a model. And here we have a model, a very simple one, okay? Now, in case, I need to move this just a moment. Sorry. In case the expected value of xj exists, then how do we calculate this? Remember, we said how do we calculate the probability, the expected value of xj in terms of its CDF, because we don't have a PDF or a PMF. I think I mentioned something about the formula. I asked you to check or review that from your previous courses. Remember, how do we calculate the expected value of xj, considering that we only know its CDF? No? You forgot? Let me see. I think it was in the first class. Here. Here it is. This is the general formula for the expected value of any random variable z in terms of its distribution function. So this formula is valid for any kind of random variable, continuous, discrete, mixed type, but it is especially useful for mixed type random variables, right? Because for the other types, you may use the PDF or the PMF. But here, since you only have a CDF, this is the formula that you have to use, okay? So it's the difference of these two intervals. In case both intervals converge, right? Because both intervals are improper integrals, right? One is from 0 to infinity, the other one is from minus infinity to 0. But we said that this has a nice geometric interpretation, which is basically the area above the graph in the positive reals minus the area under the graph on the negative reals, okay? So in case both areas are finite, then the difference of these two areas is the expected value. But in this particular case, I'm sorry, let me go back to the formula. But in this case, we have 0 area to the left of 0, right? Because it's a positive random variable. So in our particular case, we forget about this part, right? This part, region B, has area 0, so this is 0. So we only use this part, right? So we just need to calculate this with the formula we just got. So let me. Then always write it as a proposition, in fact, because this is an important result. Then, and this is going to be result number 4, proposition. If the expected value of xj given xj positive exists, then the non-conditional expectation of xj is going to be the integral from 0 to infinity of 1 minus f of xj of x dx, right? We don't need to subtract a 0 because to the left, that's why we made the sketch of the graph here. I mean, what we need to calculate is this area. So let me change the thickness. This area, say, this area is the expected value of xj. I think somebody is raising their hand. Oh, sorry, let me check again the message. It says it's possible to use continuous random variable models. Yes, but not directly. I mean, not as a model. Remember that we mentioned the decomposition theorem for random variables, right? So the models we need are for mixed type random variables. But let's go. Where is it? Here it is also. Here, we said the composition theorem for random variables. And that theorem, I hope you remember from your probability courses, says that the CDF of any kind of random variable can be expressed as a convex linear combination of a discrete CDF and a continuous CDF, okay? In our case, we need models for mixed type random variables. But yes, you can build a mixed type random variable model through a convex linear combination of a discrete CDF model and a continuous CDF model. So that's what I said. Yes, you can use continuous random variable models, but as part of the model, and use the decomposition theorem to build a mixed type. Okay? So I hope I answered correctly the question. If not, please let me know. So, so we say, okay, so this area, in this case, this area is what we need to calculate the expected value of xj, right? And this area means to integrate 1 minus this amount, because this area has as a lower limit this part of the graph, which is this part. 1 minus qj plus qj times this, okay? Because here we have nothing, and here we have nothing. So that's the reason why this integral becomes, sorry, the integral from 0 to infinity of 1 minus, let me write everything, 1 minus qj, 1 minus qj plus qj, sorry, qj, just sub-index, qj, f of xj given xj positive of x dx, right? Then we cancel this one with this one. Then we have minus, minus, right? Minus, minus. And then we have the integral of 0 to infinity of qj plus no, minus, sorry, because here we have minus times plus is minus, right? So it's going to be minus, minus, plus, and then minus qj times f of xj given xj positive and then we may factor qj, right, out of the integral. So we will have qj times the integral from 0 to infinity of 1 minus f of xj given xj is positive of x dx. But again, by definition, this is the expectation of this random variable, right? I mean, when you calculate the integral of 0 to infinity of 1 minus a CDF, and this random variable always takes values in the positive, we have again this case, right? But instead of f of xj, we have the conditional f of xj given xj positive. So this is equal to qj times the expected value of this one. So this is a conditional expectation. So this is how we get a general formula from this general formula for xj, for the CDF of xj, we obtain the general formula for its expected value in terms of qj. Remember that we know qj, or we can estimate qj from historical data. And also, we estimate this model from historical data. So we can calculate its expected value, or we can estimate its expected value. And then we have this general formula. Okay? Any questions so far? Okay. There was a comment.
I
Yes.
My question just is, but I think it's is necessarily a mass point the maximum of the claim. Yes, because I can think of it like it has a mass point on the maximum claim amount, but I don't know how to use this formula explicit in that point. I don't know if I could explain.
Okay, well, here's the formula. I mean, we have a jump here, right? Remember that the size of the jump, when you analyze the graph of a CDF, wherever you have discontinuities, the size of the jump is the probability of that point, right? I mean, if exactly on 0 you have a jump of size 1 minus qj, that means that the probability of xj being 0 equals 1 minus qj. Here we have another jump over tau. What's the size of this jump? qj. That means that the probability of xj being equal to tau, okay, is qj. Oh no, sorry, this is not qj. It's another amount, probably, no, because qj is down. Sorry, it's not qj. It's some other amount. Whatever is the size of that jump, probably this size. Let's call it, I don't know, rj, right? Then that means that the probability of xj reporting the value tau is rj. Was that the question, or?
Yes, it was. Thank you.
Okay. Another way to see it, let me erase this. Going back to what I was explaining at the beginning, let me go back. All these claim amounts, if they all have the same policy limit, let's say that the policy limit is 1 million, okay? So if there were accidents that are worth more than 1 million, here we just register 1 million because that's what the insurance company paid. And probably the client had to pay the difference, right? So probably we will have repeated values here. So that's where you will see the effect of the policy limit. because there are going to be accidents that are worth beyond that policy limit, but the company just paid the policy limit in that case. So you will have all those cases that surpass the policy limit are going to be registered as paid the maximum amount, which is tau. How would you estimate the size of the jump? Because the size of the jump is the probability that we are going to pay the policy limit. From historical data, right? Well, from all the claims, you will check what proportion of all the claims reached the policy limit. And that will be an empirical estimation of the probability of xj being equal to tau. Right? That usually is going to be a very, very small probability, even a lot smaller than qj, a lot smaller. Right? Okay. So I want to, well, we said that this is going to be a short class because I have to attend a meeting at Acatlán, but I want you to write down this example and try to apply these formulas, and we will check your solution next class, okay? So as item 5, this is going to be an example. Consider a 1-year term life insurance policy. Consider an insured amount of CJ for client J, okay? Because each client can choose a different insured amount in this case, right? But let's think about a single client. A mortality rate, because in life insurance, the claims rate is going to be the mortality rate, right? What's the probability of dying within a year? QJ. But I'm going to add coverage. That's very common with life insurance. Additional coverage. Payment of twice the insured amount in case of accidental death, okay? Because this life insurance is paid if the person dies before 1 year, no matter the cause. Could be because of illness or could be because of an accident, right? So we are saying in case death was because of an accident, I will pay you twice the insured amount. I mean, instead of paying CJ, I will pay 2 times CJ, okay? And consider probability of death in an accident kappa J, okay? So it's a number between 0 and 1. Calculate the expected value of xj and obtain f of xj, right? So with this very simple example, you will practice the concept we have been discussing. So please work on this. And of course, we are going to solve it here next class, but it will help a lot if you can try it yourself for next class. Okay? Any questions so far? Okay. Well, if there are no more questions, I'm sorry I have to leave. And see you next Tuesday. Tuesday? Yes. Okay.
Yes, Tuesday.
See you. Bye-bye.
See you.
See you.